Actually. Okay, hi, good morning. So first, some administrative announcements. If you go to the Blackboard space, you will see that now there is an assignment that I created um, regarding the evaluation of the second term. We are a little bit late for the second term evaluation, but we are in fact not that late. Just to make sure that everyone is finally on the same page. What we have done for now is the second round is pending. I will finish between tomorrow, I think today and tomorrow, the evaluation of the second round. There's nothing to worry about, but anyway, you need to have your grades. And then I have included, I'm going to show you by sharing my screen so that, how do I do this? I am going to, this. And now you're having a look at my screen, and now, okay. So in the evaluation and knowledge control, so we have the second round. Then there is a new one, which is data processing at scale, which includes a lot of things that you have already done. It includes the first steps towards MapReduce programs that you have already handed in, or you have to hand it in briefly. Data processing and analytics, the Kahoot and the presentations that we did last time, and then the first, so the one that is still pending that will come up after today is the first steps into data flow-based programming, which is 5 points. It will be a very short activity in order to complete all the activities that will contribute to have a grade for the second period, okay? And it is 25% of the general grade, and it will be in one round, okay? Because there have been also rounds in between, okay? So it will be in one round, and in that way, before we leave on vacation, you will have your second period grade, okay? Do you have questions here? Okay, and then regarding the lab, so that you have in mind what remains to be done, and I know that at the end of the semester you tend to be very busy. So after the spring break, there will be another, I believe that a brief 2 activities regarding DevOps. So the topic that we will start afterwards. So it will be a little, some aspects of execution, etc., of Spark, and then DevOps. And with that, we will have very short activities for the third evaluation, which will be 25% too. And then the final one, which has been there for a while, which is a very simple thing to do. In fact, I will ask you, I will give more details and more input so that you can really prepare the final work. It will be to write a medium like entry concerning big data processing, the problem, and how do we address this, etc. So that will be 10 points, and then I will ask you to to film a video on YouTube or TikTok, whatever you like. I don't know if you are already too old for TikTok or you are still young for, I mean, in the good age for having a TikTok. But anyway, the idea is that you will film a video on the topic, and I have even proposed some examples of people that do these kind of exercises. And with that, that will be the final work, but that will be at the very end of the semester. Okay, and with that, we will be done with respect to the lab. Okay. So again, I like to insist because my way of evaluating, it's a kind of weird thing. So it's very constructive and it has little to do with the classic way of grading. So do not worry, that's one thing. Nobody will fail, so stay calm. And so just keep keep moving and keep doing, and of course never consider uninscribing your course because you have the impression that you're doing bad. Nobody is doing bad. Okay, so just to I want to insist on that because at some point you might get like, we are having too many activities and now I'm overwhelmed and I'm going to leave the course. Do not do that. Okay. So the idea is that you build your knowledge, that you have fun, that you see new things, hopefully, and so that you end your education on a good mood, right? Okay, so questions here. So if you don't have questions, I'm going to start. So how do I do this? I have to close. So last month I have been proposing many information regarding gender gap and women in STEM, etc. Now we are in a new month, and the new month will be devoted to considering some aspects of building knowledge that are important since you are finishing your studies, and some of you already have a clear situation on what you're going to do next, and others maybe not. But what is important to consider is that at any point, so even me, that I have been around for a long time, it is important that you consider some exercises that are provided by big companies, by leading companies, and that are intended to evaluate our general knowledge on the discipline. And so today there are many entries in Medium, in everywhere, that propose activities, hints, etc., on how to prepare a professional career, and particularly when you want to apply to positions in big companies, big leading companies. So even if you are not planning to do that, it is a very good exercise that frequently you go and have a look at the type of questions and try to figure out whether you are ready or not, and you feel comfortable or not answering these questions. Okay, so me, even now, I sometimes try to open a space and I have a look just to make sure that I'm not getting very old in terms of knowledge, and that I'm on the circuit, and that I'm not having too long ears. You know, ears get big very easily. So this is why I'm proposing this kind of material. So I am proposing you will have the slides after the session. So there is a Medium entry that suggests some activities to prepare the Google Data Engineer professional exam in 4 days. So it's a good way of moving the neurons and try to challenge your knowledge. So that's one. And then a very good exercise that I always recommend to anyone who is in the domain and is active in the domain is having a look at the at material devoted to prepare the official Google Cloud certification and so to pass the exam. And so again, there are some links here that I am proposing. For example, in this exam, there is a section on designing data processing systems. So if you have a look, we have addressed some of the topics in this course. You have certainly addressed other topics in other courses. So at least try to build a map of what you have addressed in the undergraduate education, what you are maybe missing, and that you can complete. So the second is building and operationalizing data processing systems, then operationalizing machine learning models. Maybe there I have the impression that you haven't had a lot of experience in that. This is normal because the career here is more intended to systems rather than to artificial intelligence. So, but it's good that you have a look at what is being asked regarding machine learning models. Then ensuring solution quality. This is a very important topic. I will try to touch the topic by the end of the lab or the regular course, because particularly in Spark and also in Hadoop, there are groups doing testing. Okay, so testing is a huge space in systems engineering, and it is important that you are acquainted at least on the different techniques and how this is done, because, well, when we go into the real arena, well, we do not need prototypes, but we need to be sure that we have stable systems running so that many people can use them. So this is an important element. And then there is also this one, which is a Google form exam where you have sample questions, and so you can really try to see what you can answer and where you are with respect to the fundamental knowledge expected for an engineer to be comfortable with. Okay, so this is just a publicity, complementary publicity on the preparation to professional life. And there is also, of course, there is this official cloud, book, the study guide, and this is also interesting. Again, even if you are not applying to Google or there's equivalent in Microsoft, there's equivalent in Meta, etc. So almost all companies have this kind of exams, information, etc. So as I said, it's good to have these points of view, perspectives, in order to know how we are going to go into the market as products, because we are products. So how are we going to sell ourselves? Right. So so let's go back to our topics, and we are moving from Hadoop that we saw in a very general manner, but that, as I said, I was happy that you still can touch some aspects. And then now we are moving, so that's a control flow parallelization solution, and we are moving towards a data flow based solution. And what we are using in order to study this problem is using Spark, the environment, in order to see how do we design and then execute programs that are designed under the data flow approach. And of course, at the very end, we will compare and have our vision on what we have learned and seen from this. So I did in the regular course a very general overview, more or less on the TV overview of the of Spark. Today we are going to start doing baby steps on it, and but anyway, for those that uh, do not remember. So Spark in some words. Spark is Apache Spark is an open source analytical processing engine. Okay, for dealing with large scale data processing, data collections processing, which are normally distributed. And it is very devoted, as I explained in the regular course, to data processing operations that are greedy in terms of computing resources. And an example of this are machine learning algorithms. Okay, machine learning understood in the broad perspective. Okay, there you can have also numerical methods. There you can have statistical based methods. Anyway, machine learning is based on statistics and probability. You can have more algorithms related to deep learning, etc. Okay, so all these heuristics and algorithms that are very costly in terms of CPU cycles and that become heavy to execute when we have important volumes of data. This is the market of a data analytics engine, for example, Spark. Okay. And of course, I mean, the open source story is good because at some point, well, if you have an advanced use of Spark or you are founding a startup, there you could imagine making evolve the engine, and since you have an open source material, you could do these kind of things. So I also said that it was originally proposed by the University of California, MP Lab project in Berkeley, and then it was donated to the Apache Software Foundation. So by, well, already like almost 10 years ago, I'm surprised. Okay, so Spark became a top-level Apache project, and well, it has contributed to do a lot of things. It's a very cool engine to use, and it has been used to propose many interesting solutions, both top-level solutions, so for building applications, but also it is a good arena for people really wanting to go to the internal aspects of computing systems. Okay, so it depends on where you like to work. There are projects for everyone. So the architecture is very simple. It corresponds to the architecture that we have been studying in this course. So is a coordinator worker architecture. And so the coordinator, I'm describing the engine, okay? So the setting on top of which we work. So there is a coordinator, which is called the driver, and the slaves are called the workers. So what you have here, so at runtime, the driver creates what we call a context, which is an entry point to an application. Okay, and all the operations are executed by the worker nodes. Okay, so you have the driver here. The driver is a program, of course. It contains the context, the working context of the process that you want to execute. So this is the process implementing your program. And then, of course, you will always have a cluster manager that you will never get rid of that. And then the workers that, as we have seen before, you have an execution. So the job tracker would be this executor, okay? But now there's no job tracker. There is an execution environment called the executor that is installed in every worker, and it contains a cache space, and it executes several tasks. And as in the principle that we saw in Hadoop, you have the notion of job that is parallelized in several tasks. The difference is the type of tasks that we are going to deploy on top of the workers. And then while the workers are executing, they can interact among each other, which is a big difference with respect to what we have seen in Hadoop. In Hadoop, we said, okay, we have full-fledged servers. The servers do their lives as they want. And then eventually it is the coordinator, which is the Hadoop engine, that observes the execution of the processes running in the different workers. And then it is up to this coordinator to determine at which moment all the processes have finished, and then whether it should trigger the next execution. Okay, so, and nobody talks with each other. They share just information through the file system. Here, it's not the case. You have your workers, they are executing tasks, and they have this little cache here. And the cache has data. And they can interact with each other through the cache, and of course through disk. It is important to see that cache is there because this implies that they can have access to data produced by tasks that are running on another worker. So that's an important difference. And then, of course, the workers have to interact with the coordinator, with the driver, also in order to make decisions on the evolution of the parallel execution of a job, and then eventually end and terminate the execution. And well, the cluster manager is the one that dispatches the resources of the cluster. Okay, how much disk are we going to have? How much nodes are going to participate in the execution of a program? How much CPU are we going to associate to the nodes, etc. So all the physical allocation of resources will be the responsibility of the cluster manager. Okay, so it's like having, well, let's say that the driver is the coordinator and that it has an assistant that allocates all the resources required in order to execute the processes. Okay, so you can see this like that. So that's the general architecture on how Spark works. And then, well, here, in fact, this little cluster manager can have different identities depending on the environment where it is running. So it can be standalone, which means that a simple cluster manager is included with Spark and makes it easy to set up your cluster. Okay, so that's standalone. And there are other three possibilities that have to do with something that we will touch at the in the very last topic of the course. So you can have other systems that manage your cluster. Okay. And there are two very common ones. Well, there are three. Well, there's Apache Mesos, which is a cluster manager that can work both in Hadoop and then in Spark applications. So it is possible to have this type of cluster manager in order to deal with the architecture. Of course, when we are touching these kind of solutions, we are growing in terms of complexity of the cluster, and this is why we're needing a more intelligent way of dealing with the resources. Then there are, since the Hadoop consolidated, many resource managers started to appear because the environment became very complex to deal with. And so a solution was to have prepared the environment with the different tools required in order to use Hadoop. And so in order to facilitate the deployment of solutions, and a very popular one is the Hadoop Yarn. It can be also used for Spark. And then one that is the one that I would suggest really, and that I will try to introduce, as I said, in the third part, but you keep in mind, is Kubernetes, because it's an open source system for automating the deployment, scaling, management of applications that are put into containers. So as I said, in the third part, we will study virtualization, containerization, and these kinds of solutions in order to deliver solutions and deploy them on top of different architectures. And a very interesting tool in order to perform this deployment and this scaling control is Kubernetes. And of course, it is possible to have this kind of cluster manager working with Spark. And then what we are going to more or less use, because we are going today, at least for the baby steps, we are going to work in Collab, then we will move to Azure. Well, we can of course have it locally. And so it's not really a cluster, but it's simulated through threads. And well, this is a good way of testing a little bit on a local computer, and as we are going to do on Collab, and then familiarize with all the situation, and then go out of the box to other more complex deployments. Well, Spark is also an ecosystem, and it looks like this. You have a core API that you can use through different programming language. There is R, because R is a language that has been used by other communities in order to do analytics. So many people working in industrial engineering, in TI, but TI in the sense of administration, on experimental sciences, they are quite acquainted to R, with R. And so, well, we do not want to deny anyone to, with their previous knowledge, to perform parallel activity. So R is a possibility. Of course, Python, because of analytics reasons. At the beginning, Scala was popular when Spark started to emerge. So there is a lot being done in using Scala, of course, Java. And then at some point, people started to get reasonable. And many of the operations that we perform, that's something that we saw, for example, when we work with data frames, is that when you use tabular representations, first of all, tabular representations are very popular, are intuitive. They can be used to easily represent many data, even complex data. So they are there in nature, and when you use tabular representations, you have operators that look a lot like the operators of the relational algebra. And so there was a huge evolution of Spark, and they added an upper layer of representation of data that is tabular, and so they defined ways of programming using SQL-like queries. And so this is why SQL is here. Of course, it is extended, and it can be combined with imperative solutions. But this is, I mean, I don't know if you're acquainted with SQL3, but SQL3 today is that. Okay, so it's the basic algebra plus a lot of ways of joining, of aggregating, of doing a lot of things. It's more or less a programming language. So this is the spirit in which SQL can be seen here in the context of the Spark ecosystem. And anyway, that's the Apache Spark Core API, which means that you are going to use one of these languages as programming language, as host languages, and and through them you will communicate with the engine. Okay, and that's what it does. And so and then there are other layers that are intended to facilitate the analytics and the processing of specific types of data that are popular when we want to do analytics. Again, we find here Spark SQL that is connected with this. Here you will find all the possible implementations of SQL operators, well, algebraic operators, in already built in so that we can use them. In some of in the regular course, I believe I talked about implementations of join with hash join, nested loop join, etc. And similarly, you have many implementations for the other operators, and they can be executed, of course, in parallel, and so you have them built in here. In some cartridges that are already ready to use for building applications. Then something that we will not have the time to touch in this course, but it's becoming very popular, is everything that is related to with dealing with streams. Maybe I think that you are having an IoT course. Am I wrong?
Yes, we are.
Okay, well, there you have been studying streams. So there's continuous data coming from the different sensors composing your IoT farms, and so these streams of data have to be processed in some way or another, and where they become huge, as is normally expected in IoT environments, there you need processing resources. And so Spark proposes very interesting solutions in order to deal with streams. So all the parallel ingestion of the streams, and then parallel processing of these streams in a very efficient manner. So there's a cartridge devoted to this. Then, as I said, an important client of parallel processing is machine learning. So Spark provides it's like scikit-learn in Python. So there you have almost all the classic machine learning algorithms used today to do analytics. Well, in the same way, in Spark ML lib has built-in operators in order to use them for doing machine learning activities. So that's the other cartridge. And then, of course, we are in the area of graphs because many um, data-centric problems are addressed using graphs. And so, sorry, and so Spark has a cartridge only devoted for playing with graphs in a very interesting way. And so all these cartridges compose the minimum Spark ecosystem. So if you Google a little bit today on the architecture of Spark, you will see that it's a huge environment with many cartridges and solutions, and almost every cartridge is referring to a startup that is willing to evolve, etc. So it's quite complex, but this is the stable, if you wish, the stable ecosystem elements that we can consider regarding Spark. Now, how does a Spark program look like? Well, it's important to consider two things. In any case, you need to rely in something, a system that will deal with the data. Okay, and when we talk about the data in this kind of environment, we are talking about how are these data going to be distributed across the cluster. Okay, how am I going to ensure guarantees around the data? So I do not want to lose data, for example, and I want the data to be available all the time when a process needs them. Okay, so that's one thing. And the other thing is that in the same way as in Hadoop, these kind of solutions are avoiding as much as possible to transmit data across the cluster, because we all know that transmitting huge volumes of data is risky and is costly and can create a lot of overhead, particularly because there is an element that always puts us in trouble, which is the network. Okay, we can never rely on the network. So if there are connection problems and we are transmitting data necessary to execute a process, a parallel process, we are inserting a lot of instability on the execution. So the idea is to figure out how to distribute the data across the cluster, that the data lays where it is. Of course, it will be costly. Of course, it will take time, etc. But we are supposing that that process of distributing, etc., is done previously. Okay? And once you are sure of that, then you are going to have your Spark engine and you are going to write your programs and execute your programs. Okay, so this is why this thing is here. And in the regular course, we saw that in the case of Spark, they well, first of all data are represented in the core engine. Then we will see that there are variations, but in the core engine, data are represented as RDDs. Okay, so that's the data structure that they use, and these RDDs are reliable, are distributed, etc. Okay, so that's here. And then there are two elements to consider. First of all, I'm going to tackle the program. So you have a program with instructions in some programming language, and you are going to use the libraries provided by Spark in order to express operations on top of your data. And there are two types of operations, as we saw in the regular course. There are transformations. So it's always the same. Remember, this is something that you have to always remember. Anytime that you are talking about data, you are talking about a knowledge representation. The knowledge representation says the data structures used in order to represent your data, so the data types, and then the operations associated to the data. Okay, and of course, some properties that you can associate to the data. So these three elements are always there in any data-driven solution. So anytime you will get in face of a data-driven problem, the first reflect that you have to do is which are the data structures used in order to represent the data, and which are the operations that are expected to be applied on top of this data, and then which are the properties that I have to guarantee when I am applying these operations. Okay? If I don't have any properties to guarantee, then I will have problems. Okay, so there is always some guarantees to be considered. And if they are not explicit, you as engineers have to track them from the user, from the characteristics of the data, from the specification of the problem, but you always have to exhibit these expected properties. Okay, so in this case, it is the same. The first data structure, the only data structure that we are going to deal with is this notion of RDD. I will get into the RDDs in 1 second, okay? So, and on top of this data structure, we can apply two types of operations, transformations and actions. Okay, so that's these are the rules. And the properties is that data is immutable and it's fault tolerant and is distributed. Okay, so that's you see the three elements. Now let's count words as we have been doing for the last month or something. So how would the counting word program would look like? Well, the first thing, well, this SE is you are going to create this Spark context that will contain your job. Okay, so here it is not exhibited. Well, the instruction creating the context is not exhibited, but I'm using it here. Okay, so I have a context, and the first thing I'm going to ask is to retrieve the data I am going to process within my program. Data can come from local disk, from your distributed file system, or from any other store. For example, MongoDB or whatever you like to use, okay? Vertica, MySQL, Oracle, whatever, okay? So there is a repository of data, and so through your context, you are going to retrieve the data that you are using in the program. Then this story of MapReduce is always there, but here it comes in another flavor. The first thing that you are going to do is, well, we are assuming that we have textual files, so we're going to go through the lines and split them according to the space, no? To empty space. And what we're going to do is we are going to filter words, so terms, and of size greater than 0, okay? Which means that we are not observing characters that are not tokens, no, that are not words. And then we are going to do the thing that we are all are used to do. For every word, we are going to associate 1, and then we are going to reduce by key. So instead of saying that delegating the ordering and the shuffling part to the engine, here we have to do this explicitly, okay? So we are asking the engine to order, well, to reduce by key, which is get all the tuples that have the same key, and then do the summation of the of this. No? And then the result, we can do many things. In this case, we are saving it again on the file system, but we can do other things in Spark. Here, it's just the first way of using it, which is close to what we have been doing in Hadoop. Now, how I'm going to skip this first. Okay, so if we do the pipeline, the execution plan of the program, it can be represented as a directed acyclic graph that looks like that, like this. So your data come from the HDFS. It is splitted into lines. It filters the words. Then it validates the existence of a word. Then it creates pairs and it does the it creates pairs and then it does the summation, and then data go back to the HDFS. Okay. So what is, in your opinion, the interest of having this representation of the program as a first citizen? Why is it interesting, for example, in databases to have the execution plan explicit? What do you think? Please, Mauricio.
So teacher, you are asking why is the interesting part about having like more control in every step of the
Okay, we have more control,
yes.
which means what is more control?
Especially the what are we going to map and what we are going to reduce. So what in which way we are going to reduce it. In this case, we reduce it by key, is what I can see, and also the way we process every line. Maybe it can be another one, and also how how is going to be the pair key, how it's going to be defined. I believe that is the control part.
Okay, so your point is that if I have this access to this directed acyclic graph, me as a programmer, I will see how all these steps are working.
Yes.
Okay, so that's one thing. What else? Remember that this is a first-class citizen structure. What happens when we have first-class citizens in our systems in general? When we have first-class citizens in our systems, this means that we can operate on these elements, on these items. So in the case of an execution plan, or in the case of this directed acyclic graph, this means that a metaprogrammer could modify this. I can reorder the flow of this. I can act on what is being done in each of these steps. For example, here, for example, in filter is a general operator. But imagine that we have a toolkit of implementations of filter. Here I can, as a metaprogrammer, say which is the implementation of filter that I want the system to use in order to execute my command. And so, if you think further, this opens the possibility of optimization. So you will have your program written. It will be materialized as this directed acyclic graph. And you can have a process that will have a look at this directed acyclic graph and can say, well, maybe if these two lines are exchanged, you can have better performance. And then if you reduce by, you hear this person said that she wants to reduce by key, but what about reducing with another strategy? You see, and all these modifications can be done automatically and have an optimized version of your program that is then executed. And so it's like when we write queries in SQL, we never think about the optimum way of expressing our query. We express our query in the way we reason, etc. And then we deliver to externalize to the DBMS the burden of rewriting our query such that it will run faster and we will have better, good performance when obtaining results. This is the same case here. You will have your program and then you can go through an optimization phase delivered to the engine in order to optimize it and run it faster. And more than that, you can intervene in the execution of your program and have a full control, an external control of the program. Is this clear? So the question is, why do we need to do that? I'm telling you, yes, we have a canyon and we can hit something on the moon, etc. But do we really need that? We do because of performance. Okay, so depending on the situation of the cluster, in the situation of the program, the distribution of the data. So at some point, it might be interesting that we reorder the activities, etc., or the engine in order to have good performance. That's the thing. And then you will see later on when we will have a touch on testing is that when you do testing, you can operate on the DAG in order to test the accuracy and the performance of your programs. But that's an advanced thing to do, and this is also useful through the DAG. Okay. Back here, and so we are in the blue thing. So the question is, what do I have the right to use as operator in order to process my data processing operations? Note that here we are just using operators. We do not longer give the code in order to filter the words, in order to build the tuples, and in order to do the summation. Here, it's just operators that we are calling that are already programmed so that the counting words or whatever can run, okay? So here we are not going to implement any function. We are just going to apply operators and order them such that we obtain the result we want. And so As I said in the regular course, um, the first thing that we have to think about is exactly that. What are the operators that I can apply on my data? Okay, it's more or less the same as learning SQL, no? Which are the operators that I can apply on relations. Okay, so there are seven groups of 1, 2, 3, 4, 5, 6, 7. Yes, 7 groups of operators. So there are families of operators called transformations that we can use. We have mapping, which is correlation, and we have two types of operators, map and flat map. We have filtering, we have one filter, and we can eventually do our own filters. We have grouping, grouping by or grouping by key. We have set operations on sets, union, intersection, subtract, and distinct. We have aggregations. We have join. So I don't know, well, today we won't have time, but when we will see joins, there are several possibilities of joins. No? So inner join, left outer join, right outer join, full outer join. And these ones are included, for example, in SQL3. No? And then sorting order by key or order by normal. Okay, so these are the families of transformations that we can apply on top of RDTs. Let's have a look at internally how this all works. First of all, as I said, so you have these resilient distributed data sets. So it's a collection of elements, okay? An RDD, it's a collection of elements, and which elements? You can have arrays, you can have tables, you can have data frames, as we studied in pandas, for example, or in R, there's the notion also of data frame, or collections as from MongoDB, okay? All these data types are can be RDDs, okay? The property is that they are distributed on top of different machines and that they are resilient, meaning that they recover from failure. So what happens is that you have this distributed data set. So you have little containers grabbing all these possible types of data, okay? So you have them like this, lying in some persistent support, and you are going to distribute them, so fragment them and distribute them across different machines. So there's the notion here and forever we will find this notion of sharding, of fragmentation that will operate in order to distribute the data across the clusters. And so when you have an application, so you will have the driver that contains the context where your application is going to run. Every node will have an instance of your application, okay? And then every node will have pieces of the RDD. And your Spark application will run on top of these portions of data that are lying in the different nodes, the complete program. Okay, and then as I said, eventually there is communication here if they want to see partial results, but normally it works like this. So reminder of RDD, as I said at the beginning, they're immutable. They split in partitions on top of several nodes, and they can be of any data type associated to Python, Java, Scala objects, or user-defined classes. They can persist in memory. They auto-recover, so this means that if one node goes down for some reason, it can, after when the node comes back, you will not lose information. So inside your data, your RDD, you will have key value tuples. false. Okay, the thing is that they are grabbed on by these RDDs. And as we said, we can apply transformations and actions. Now, transformations, the principle is very easy. You will have an RDD, you apply a transformation, and the result is another RDD. Okay, so the particular aspect of the semantics of any transformation operation is that it is applied on top of an RDD and it produces a new RDD. Okay, that is again distributed and it's immutable and so on and so forth. Examples today, I think that we will not have really time to go into deep into the matter, but mapping, so correlating or filtering are examples of transformations. So what happens if we have a look at the architecture is that the Spark driver running the application will have access to an initial RDD. The different nodes will perform the transformation on the portions of the RDD, and they will produce a new RDD which will be fragmented across the different nodes of the cluster. And the Spark driver will have knowledge of everything, of the initial RDDs and where it lies, on the type of transformations that were executed on top of the RDDs, and on the resulting RDD, the way it is fragmented and whether it lies in memory or if it went to disk. So this one knows everything. So example, if we would like, for example, we have an initial set of numbers distributed across four clusters. So we have 1, 2, 3, 4. These are our numbers. And we want to multiply these numbers by 2. Multiply by 2 is a transformation. So it is applied on top of these different RDDs, and the result is a new RDD where every element is the multiplication by 2 of the initial RDD. And we have a new RDD. It looks dull, but then it gets much more complex. Here, the important thing to remember is this notion of new RDD. Since here we are reasoning about data, we have to be aware of the data that we produce and how it lies on the cluster so that we can make decisions on how to do the next steps of our program, write the next steps of our program when we write it. We could have, for example, another case, which would be, let's filter the even elements of a set of numbers. No? So we would have, for example, an array that goes from 1 to 1K, and then we are going to say that we are going to parallelize this array. When we say that we parallelize this array, what the engine does is it fragments across the different nodes. How many we can specify as programmers, how many nodes we want to contribute in this allocation of the data. And then we define a function that says that if a number is even, it is true, and if the number is not even, it is false. And so in our program, what we say is that we are going to use the filter is even. Of course, here I'm using a functional programming approach. And so what it does is that it goes through the set of numbers, it looks at each of them and to see which is even, and those that are Boolean are contained in the new RDD, which contains 3 elements. This is the principle. I mean, I'm just insisting in the fact that out of an initial RDD, you produce a new RDD. And then actions. Actions are when you specify these transformations, in fact, the engine doesn't do anything. It waits until you do an action. And when you do an action, when you ask for an action, then it starts the execution on the different nodes. This is called lazy evaluation, and it is intended to improve performance. Okay, so what happens is that it involves both the driver and the node. So all the nodes are ready with their activities. They know what to do. They know the data too, but they do not anything. And then when an action comes, the driver says, now you execute, and everyone executes, and well, the result is done, or the result of the transformation is produced. Okay. And then they communicate back to the driver in order to tell it that they could perform correctly their transformation. I wanted to show you this rather. So the lazy evaluation is like that. It's like when you go to the restaurant, what happens is that the waiter receives the order, but the order is just in paper, okay? And it is only when she or he goes to the kitchen and gives the order that the cooker will start performing the order, okay? So this is a fancy restaurant. If we go to buy tacos, sometimes what happens is give me one of that, give me one of that, and already while the order is coming, the tacos are already being prepared, okay, and then they are brought. So in the moment the order is executed, and this happens almost in every programming language. When we do a command, for example, in the interpreted version is very evident, no, because you have a cell, you have your command, you execute, and it is executed, and you have the result. Okay, so in Spark, this is the opposite. Everything will be done in intention, and it will be only when an action comes that all the operations will be performed. Yes, so how much time do we have? Almost nothing. I'm going anyway to introduce the hands-on, even if I will ask you, I will send a message to give instructions on how to do the hands-on. We are going to do it asynchronously so that next time we can do more interesting things. You will see it is very easy. So, okay, so I'm going to share here the chat. So here you have the link to the baby steps into Spark. That, as I said, we're starting in Colab, and then we will move to other settings. So the baby steps are done as follows. First of all, we are going to configure. Spark needs the Spark engine needs a Java environment in order to be executed. Okay, so do not get lost. There is Java there, even if we are going to work in Python, because here we are going to install the engine, and the engine requires these components. So the first part, I'm going to describe what the notebook contains, and then you do not have to do it right now. I will send instructions on how to perform this and how to prepare for the next lab so that we can do more interesting things. So the first part is the configuration. We are going to define three variables: the version, it has dependencies with Hadoop. So the Hadoop version, it is lying behind the, the implementation, the engine, and then an OpenJDK version. Okay. We will prepare our variables, and then we will install. Okay, and you will see what you can do it once. It takes a little bit of time to install this, so not a lot, but it takes time. And once you have installed, then you are ready to start working. So in our case, we are going to work with Python, and Python, in fact, is a wrapper that calls behind Java instructions. Okay, so at the beginning it was not a real host language, and this is why we need Java behind. So we need to configure this little wrapper that will let us work in Python. And here, what it is interesting that we didn't see in the Hadoop version is that here you can define some elements regarding the resources that you are going to allocate to, particularly to the driver, and then eventually the number of nodes that you can use. So here what we're saying is that the driver will be allocated with 8 gigabytes. And so, well, we configure this wrapper of Spark that in fact will let us submit Python programs to the driver. Then you will have a part of initialization of Spark, where you will have well, here it's we are simulating with threads. As I said, eventually we will move to a cluster, but here well, once you create your context that you will use in order to work with Spark, you are here creating a context using PySpark. And so here you have the context, and the context in fact tells you, has some metadata, which includes the version, the master, and here we are having all the nodes, even if our nodes are threads. And then we have the application name, which is the shell of PySpark. So that's a lot of configuration. Normally, what I ask you to do is to draw the architecture that is behind. What we will do in this case, it is a little bit weird. We are going, I'm going to distribute the architecture myself, so that once you configure this, you have in mind the picture of what is going on behind the scenes with this preparation of the environment. And then what comes is the example, which is a very simple thing. We are going to count the number of rows in a file. And now I'm realizing that we have a little bit of time because today is the lab. So anyway, we're going back to the I continue with my description, and then we come back to the installation. So here it's just really to see how it works. So we have our context, and we retrieve a README that is already lying in our space, and we count the number of rows. So as I said, we do not longer have to write any map, neither a reduce function. We have just to be acquainted of the operators, the transformations that we need in order to do what we want, and call them. So that's the first example. The second example will be using filter and providing a lambda function, which is part of the power of Python, in order to count the lines. No? And then I will, well, we will have a look at the a collect, which is an action that really performs the operation. So that's the first part, and then the second part is related to starting getting really acquainted. So this was just control and see that everything works fine. But then the real thing is that we are going to start studying the different aspects of the engine of Spark, which means understanding how to process RDDs with testing the different transformations that are provided by the environment, and then having a look on how what happens with actions, and eventually going to the painful aspect, which is these decision makings that I have introduced in the regular course, which is managing cache, etc. But in this part, you have what we will do is having a look at the RDDs, applying some functions, and then understanding how these operations look like in Spark. Here I missed one. Okay, so are you already connected to the notebook? Good. Well, so let's do the first part, and I'm going to execute everything, right? Because I want to explain, but you can go step by step. So maybe you can decide to execute only until the initialization of Spark, and then you stop, and then we can go step by step. As I said, the part of the installation might take a little bit of time, just a little. Well, a little bit, yes. I don't know how you are doing with from your side, but yeah, 56 seconds. So if we start with the PySpark example, I'm going to go step by step through it. Of course, as I always insist, we can read either locally or through an HDFS file or from another store. Here we chose the simplest way to do this. And if you have a look here at sample data, you will see this README. Okay, so this README is a textual file. So what here using this is very important, okay, that you never forget this. In order to start every time using Spark, you need to have your context, okay? So the very first thing that it's important to be aware of is that, so first things first, we create the execution context, okay? Spark context. And we keep it as a variable, okay? And again, as I said, this variable has metadata, and the metadata tell us about the type of execution context that we are using, that we will be using in order to write our operations. So using my Spark context, what I'm doing is fetching the data, okay? And as I said, here, well, I already have this .md, and you can see it here is a textual file. And now what I want to do is count the number of rows that it contains. So the text file that is lying in this variable, and which is an RDD in fact, I'm going to apply the operation count on it. And then it says that I have 19 rows. So this looks much more as the experience we have with data frames rather than the experience we have with MapReduce. Right? So here you have the variable with your data, and then you start playing with the data. And again, remember, it's immutable because you have everything, but for the time here, you have everything in main memory, and the data in the file system remains immutable out of the operations that we are applying on top of it. But here we are not modifying, but eventually if we do, we just modify what lies in memory, and then it is up to us eventually to say that we want to store it, okay, either in cache, in memory, or in disk. Now we can, for example, print the first line of the input. You see, it looks much more as what we did in pandas with the data frames, no? So you can see here that it corresponds to what we're saying. This is the string of the first line. We can, for example, count the number of lines that contain the word dataset, which is very similar to one of the exercises, the last exercises that we did in MapReduce. But here it looks like this. So you are going to use your text file. You are going to filter your lines using the string dataset. And then once you have it, you have the lines that contain this string, then you count them. And now we are going to use the function collect, which means extract from the Spark cluster the lines containing the word dataset. What is the difference between the first and the previous one? Yes, please.
Teacher, could you repeat it, the question, please?
Yes, the previous um, instruction said that I want to count. Well, I used this README, and then I counted the number of lines that contain the string dataset, right? Knowing that the text file is lying in memory. Whereas here, I am saying that I am using this operation, collect, which in fact is extracting from the Spark cluster the lines containing the word dataset. And my question is, what is the difference between this one and this one?
About the count and the collect functions.
About the fact that I programmed this counting of lines that contain dataset in the file I provided as input rather than this.
Okay. Well, I think the second one is already partitioned in different clusters, and the first one is
The
only
first
getting
one too.
from the
The
local.
first one too.
The first one. Mhm. Entonces, no sé.
In fact, here I'm going to here I retrieved the data from somewhere and I used it to play. Whereas here I am going to the cluster and looking for, without putting this into memory, going to the cluster and seeing which are the pieces of strings that contain the substring dataset. You see here, I never collected any textual file to memory. I just went back to the cluster and and analyzed the data. Yes, yes, Marina, please. Do you have your mic open? I thought I had a question. No question. Yes, I know that because here it says that you are having issues with internet. I mean, you come back and forth from my point of view. What we're going to do is we're going to stop here. We will go back to some of the aspects, these little last aspects that I need time to explain. And then, as I said, you will receive instructions to finalize these really baby steps of the initialization to Spark. And then next time we will do a much go deeper into the matter with a lot of exercises playing with transformations. Today was, as I said, the baby steps to start touching a little bit how programs look like in Spark. All right, so do you have questions before we wrap up? What my question was, the first one, okay, memory. It went, wait a minute. As you know, I have to, to I'm going to stop sharing and I have a look at you. Okay. In the first one, we keep it in memory in order to check it if the substring is there. And yes, right. Everyone can see the chat. Okay, so let's wrap up here if there are no further questions. And oh yes, we still have the two regular course sessions, right? So that we can go into theory and into the details of that, and then we will have lab for testing what we discuss on regular course. So if there are no more questions, I'm going to stop recording.